Hello friends, I welcome you in lecture number 10 on elementary analytic functions. So from last 3 lectures we are discussing this trigonometric and hyperbolic functions of complex variables. So in this lecture also we are going to discuss some properties and examples on these trigonometric and hyperbolic functions. So let us start with this property. Sin hyperbolic z and cos hyperbolic z are periodic functions with the same period 2 pi I. So this is very interesting property. If we consider real hyperbolic functions, then these are not periodic. But for complex hyperbolic functions, we have periodicity with them. So that is the difference between real and complex hyperbolic functions. Real hyperbolic functions are not periodic, but complex hyperbolic functions are periodic. So we first show that sin hyperbolic z is periodic function. So for that we start with this identity. We know that sin iz is nothing but I times sin hyperbolic z. So from this we can write sin hyperbolic z is nothing but 1 over I sin I into z, and 1 over I is nothing but minus I. So minus I sin iz. So this is the relationship between complex sine and complex hyperbolic sine function. Now we want to prove that sin hyperbolic z is periodic function with period 2 pi I. So we have to prove that sin hyperbolic z plus 2 pi I equal to sin hyperbolic z for all z. So if we can show this, then it is proved that sin hyperbolic z is periodic function with period 2 pi I. So we start from left hand side and let us see whether we can show that it is periodic function with period 2 pi I. And we will of course use this identity. So we start with sin hyperbolic z plus 2 pi I, and using this identity we can write this as minus I times sin of z plus 2 pi I into I. We are using this identity. We can write here by using number 1. So sin hyperbolic z is minus I sin iz. So instead of z we have z plus 2 pi I. So we replace z by z plus 2 pi I in number 1. So now this I can rewrite as minus I sin of iz plus 2 pi I square. And as we know I square is minus 1. So this we can rewrite as minus I sin iz minus 2 pi. Now because sine function is odd function, we can take negative sign outside. So this is minus I into minus 1 sine 2 pi minus iz. So this is now minus I into minus 1, that is I. And because we know that sine is a periodic function of period 2 pi, we have sine of 2 pi minus iz equal to sine of minus iz, because we know that sine is a periodic function with period 2 pi. Okay, we can write sine of z plus 2 pi equal to sine z for all z. So instead of z we have minus iz here. So sine of 2 pi minus iz equal to I times sine of minus iz. Now because sine is odd function, sine of minus iz will be equal to minus of sine of iz, because sine is odd function. So sine of minus iz will be equal to minus of sine iz, and we have this I in the product. Now using identity 1, we can write minus I as it is, and we can write sine iz equal to I times sine hyperbolic z. Okay, we are using the fact that sine iz is nothing but I times sine hyperbolic z. So this is now negative of I square sine hyperbolic z. Negative of I square is 1, because this is negative sign and I square is minus 1. So it is sine hyperbolic z. And negative negative positive, so we obtain sine hyperbolic z. And this is true for all z. So what we obtain? We obtain that sine hyperbolic z plus 2 pi I equal to sine hyperbolic z for all z. So therefore we have shown that sine hyperbolic z is periodic function with period 2 pi I. Similarly, we can show that cos hyperbolic z is also a periodic function with period 2 pi I. So let us try to prove that part, cos hyperbolic z. So before proving that part, we should write this identity that we are going to use. Cos iz is nothing but cos hyperbolic z. So we give this number 2. And we start with cos hyperbolic z plus 2 pi I, because we want to prove that cos hyperbolic z is a periodic function with period 2 pi I. So we start from this cos hyperbolic z plus 2 pi I, and we will show that this is nothing but cos hyperbolic z. So using this identity, I can write this as cosine of I times z plus 2 pi I. If we have z, then here I into z. So instead of z, we have z plus 2 pi I. So that is multiplied with I. This I can rewrite as cos of iz plus 2 pi I square. And because I square is minus 1, we have cos of iz minus 2 pi. Now cos is even function, so these two are equal. If I take negative sign, instead of iz minus 2 pi, I have 2 pi minus iz, because cos is even function. So either cos of minus z or cos of z, both are equal. So iz minus 2 pi I rewrite as cos of 2 pi minus iz. Now cos is periodic function with period 2 pi. So this is equal to cos of minus iz. Okay, here we are using the fact that cos z plus 2 pi equal to cos z for all z. So instead of z, we have minus iz. And because cos is even function, this is nothing but cos iz. And as we know, cos iz is nothing but cos hyperbolic z. Using this equality, here also we have used identity 2, and here also we are using that identity 2. So this is true for all z. So what we have shown, cos hyperbolic z plus 2 pi I equal to cos hyperbolic z for all z. So this shows that cos hyperbolic z is a periodic function with period 2 pi I. Okay, so thus we have shown that hyperbolic cosine and hyperbolic sine are periodic functions with period 2 pi I. Now we consider this question, or you can consider it as example. Solve the equation cos z equal to 5. So to solve this equation, we are going to use definition of cosine function. So we start by writing definition of cosine function, and given that cos z is 5. So as we have discussed, cosine z is nothing but e to the power iz plus e to the power minus iz over 2 equal to 5. So therefore e to the power iz plus e to the power minus iz is nothing but 10. Now here I have e to the power minus iz. So if I multiply whole equation by e to the power iz, I will have e to the power iz square. Here e to the power iz into e to the power minus iz equal to 10 times e to the power iz. So we are multiplying this equation with e to the power iz. Now this is going to be e to the power 0, which is 1, and this we consider on left hand side. So this is e to the power iz square minus 10 times e to the power iz plus 1 equal to 0. Now if you observe this equation, it is nothing but quadratic equation. Just a minute, I have to rewrite again. E to the power iz square, this is taken on left hand side, 10 times e to the power iz plus this is going to be 1 equal to 0. So this is nothing but quadratic equation in which variable e to the power iz. So I write which is quadratic in e to the power iz. And we know how to write down the solution of quadratic equation. So e to the power iz equal to minus coefficient of e to the power iz, that is minus 10, plus or minus under root b square minus 4ac. b means coefficient of e raised to iz, which is minus 10, minus 4a means coefficient of first term, which is 1, c means last term, and this is 2 divided by a is 1 here. So now we simplify this. Therefore e to the power iz, this is going to be 10 plus or minus, this is going to be 100 minus 4, that is 96 over 2. So therefore e to the power iz equal to 10 plus or minus this 96 I can write as 16 into 6 over 2. So therefore this simplifies to 10 plus or minus, this is square of 4, so under root of 16 is 4, and under root 6 divided by 2. So therefore e raised to iz, now 2 will cancel out, so here we have 5 plus or minus 2 under root 6. So we have e raised to iz equal to 5 plus or minus 2 under root 6, and we are interested in z, how to find out z. So here we can use the definition of log z. We know that if e raised to z equal to w, then this w, if e raised to w equal to z, then w is called log of z, or w equal to log z if e raised to w equal to z. So here using this we can write that I into z is nothing but natural logarithm of 5 plus or minus 2 under root 6. Where log ln denotes the complex logarithm. Now from this we obtain z equal to 1 over I, and this by the definition of logarithm, this is nothing but log of absolute value of 5 plus or minus 2 under root 6 plus I times argument of 5 plus or minus 2 under root 6. So now this 1 upon I can be written as minus I, and log of 5 plus 2 root 6 and 5 minus 2 root 6. So 5 plus 2 root 6 and 5 minus 2 root 6 both are positive real numbers, so their absolute value is the numbers itself. So absolute value of 5 plus 2 root 6 is 5 plus 2 root 6. Absolute value of 5 minus 2 root 6 is also 5 minus 2 root 6 plus I times argument of 5 plus or minus 2 root 6. So we have to decide the location of 5 plus 2 root 6 and 5 minus 2 root 6. So suppose this is xy plane, and here suppose 0, 1, 2. Now if we talk about 5 plus 2 under root 6, so it is going to be 5 plus 2 root 6 will be on positive x-axis somewhere. So we don't require exact location. Suppose this is 5 plus 2 under root 6, and if we consider 5 minus 2 under root 6, then it is also on the positive real line, 5 minus 2 under root 6. So both are on the positive real line. So by the definition of argument, the vector made by this vector made the angle made by 5 plus 2 root 6, this vector, the vector representing 5 plus 2 root 6 is on x-axis. So the angle made by the vector representing 5 plus 2 root 6 is 0. Similarly, angle made by the vector representing 5 minus 2 under root 6 is also 0, because both are on positive x-axis. So argument is going to be 0 plus 2n pi. So here we write 2n pi, where n belongs to z. So now we can simplify this. So therefore z equal to minus I ln 5 plus or minus 2 under root 6 plus 2n pi I. And if we take minus I inside, we have minus I log 5 plus or minus 2 under root 6 plus 2n pi I into minus I. So therefore z is nothing but minus I log of 5 plus or minus 2 under root 6, and this is going to be minus I square, and minus of I square is nothing but plus 1, because I square is minus 1. So we have 2n pi, where n is any integer. So this we can rewrite as z equal to 2n pi minus I ln 5 plus or minus 2 under root 6 n belongs to z. So here this log is nothing but real logarithm. So in this way the solution is nothing but z equal to 2n pi minus I times log of 5 plus or minus 2 under root 6. The values of z which satisfy this equation cos z equal to 5 are nothing but z equal to 2n pi minus I log of 5 plus or minus 2 under root 6. This is real logarithm, so you can find its value using scientific calculator also. Next example, find all solutions of cos hyperbolic z equal to 2. So here also we start with the definition of hyperbolic cosine. Cos hyperbolic z is 1 by 2. Therefore, by the definition of cos hyperbolic z, e raised to z plus e raised to minus z by 2 equal to 1 by 2. And we can cancel out this 2 with this 2. And e raised to z plus e raised to minus z is 1. Now we multiply this whole equation by e raised to z. So we have e raised to z square plus e raised to z into e raised to minus z equal to e raised to z. So we can see this is now e raised to z square minus, I am taking this minus on left hand side, so minus e raised to z, and this is going to be e raised to 0, that is 1. So this is quadratic equation in which variable? E raised to z. Instead of z we have e raised to z, and if we compare with that standard form of quadratic equation ax square plus bx plus c equal to 0, we have a equal to 1, b equal to minus 1 and c equal to 1. So therefore the solution of this equation is e raised to z equal to minus of minus b, which is so minus b. So minus and b is minus 1 plus or minus square root of b square, which is minus 1 square minus 4 into a into c, which are 1, divided by 2a. So therefore e raised to z is 1 plus or minus, this is going to be 1 minus 4 by 2. So therefore e raised to z is 1 plus or minus under root of minus 3, and under root of minus 3 can be written as 3i square, and therefore we obtain e raised to z equal to 1 plus or minus under root 3 times I divided by 2. So this I can rewrite as 1 by 2 plus or minus root 3 by 2 into I. Now using the definition of logarithmic function, we know that if e raised to w is z, then w is nothing but log z. So here we have e raised to z equal to this. Therefore z equal to log of this 1 by 2 plus or minus root 3 by 2i. So by the definition of logarithm, log of this number equal to log of absolute value of this number plus I times argument of 1 by 2 plus or minus root 3 by 2i. Now if we take modulus of these numbers, either we consider positive sign and negative sign, then modulus is nothing but square root of real part square, which is 1 by 2, that is 1 by 4 plus square of imaginary part. So square of imaginary part is 3 by 4. So we are using just the definition of absolute value, square root of real part square plus imaginary part square. And because this is both are positive, we reduce this modulus plus I times argument of 1 by 2 plus or minus root 3 by 2I. Now this is nothing but 1 by 4 plus 3 by 4, which is 4 by 4, that is 1. So log of 1 plus I times argument of 1 by 2 plus or minus root 3 by 2 into I. Now log 1 is 0. This is real logarithm. So we have z equal to I times argument of 1 by 2 plus or minus root 3 by 2 I. So all we have to decide is argument of 1/2 plus or minus root 3 by 2I. So if we consider positive sign here, there are two possibilities, either positive or negative. So if we consider positive sign, we have 1/2 plus root 3 by 2I, which is in the first quadrant, as you can see in this figure. 1/2 plus root 3 by 2I is in first quadrant. And if you find out theta by taking imaginary part divided by real part, you will have root 3 by 2 over 1 by 2, so which is root 3. So tan theta is root 3 for both of these numbers. So the value of theta for which tan theta is root 3 is pi by 3. So this angle is nothing but pi by 3, angle made by this vector with positive x-axis. Now another number is 1 by 2 minus root 3 by 2I. So it is nothing but a reflection of this number with respect to x-axis in fourth quadrant, because 1 by 2 as it is, and we have root 3 by 2 here, here we have minus root 3 by 2. So we are interested in this angle. So as we know, this angle is pi by 3. So this is also pi by 3. But because we are going in clockwise direction, we have to consider minus pi by 3. So argument of 1 by 2 plus root 3 by 2I is pi by 3. And argument of 1 by 2 minus root 3 by 2I is minus pi by 3. So we can combine these two. Argument of 1 by 2 plus or minus root 3 by 2I, this is equal to, we have two possibilities, 5 by 3 and minus 5 by 3 plus 2n pi. So we can write plus or minus pi by 3 plus 2n pi. So this is nothing but argument, and we substitute here. We put this value of argument here. So we have I times plus or minus pi by 3 plus 2n pi. So this is equal to, if we take pi common, so we have 2n plus or minus 1 by 3 I into pi, n belongs to z. So these complex numbers are nothing but solutions of given equation. So in this way, using these definitions, you can prove this type of problems. So what we obtain, cos hyperbolic z must be equal to 1 by 2 for this z. So this is the solution of cos hyperbolic z equal to 1 by 2. So you can put value of z in given equation, and you can check whether our solution is correct or not. So this is all about today's sessions. I hope you like this lecture. If you are watching this channel first time, kindly subscribe this channel for upcoming lectures. Thank you very much.